All right, thank you very much. Yes, so this is going to be slightly different as a talk between the talk that you saw yesterday. I would like to actually be on the internet. Thank you very much. And so yesterday we had all the faith and preaching and sermons. Today it's going to be much more direct and actually get down to some of the brass tacks. So for those who don't know, what is Co-dfns? Basically, what we're trying to do with Co-dfns is create a tightly integrated compiler that is essentially a drop-in replacement for the Codfns function in Dyalog APL, and make that a platform for you to scale APL applications into new domains. I want to improve programming education and to facilitate further research into the APL language, but also basically allowing for the APL programmer to easily, relatively speaking, easily get to their GPU computing power without having to become necessarily CUDA or OpenCL experts or anything like that. Let them work inside of APL and do their work and sort of bring APL into that modern hardware and future problem space. So basically, we're going to be doing a lot of hands-on demos here. So one of the biggest things we've been working on this year with the compiler from last year was really trying to make it much, much easier to install. So the basic idea behind installing Co-dfns now, as it stands, is you're going to need a system compiler, Visual Studio on Windows, GCC on Linux, your Apple developer tools with Clang on Mac, and then you'll need to install ArrayFire, the CUDA toolkit if you want to use your NVIDIA GPU and the CUDA backend, and then after that, to set things up, you basically have a single Co-dfns namespace here, and you create a little build directory that you go into, and then you'll need to copy this DLL from your CUDA toolkit, and then you're done. You're ready. You're basically ready to start playing after that. And once you have that ready, if you're on Windows, you'll need to make sure you point to your Visual Studio path and set your backend library to what you want to use. So right now I'm using the CUDA backend, and then you're all good. So at that point, you can run the compiler. Inside of your interpreter, it'll compile stuff, and you get a namespace that allows you to run some data, and it works like a regular namespace, with the caveat that don't change anything in the namespace. Don't edit it, things like that. However, one of the benefits here is that the namespace works just like a regular namespace. It's just like a Codfns namespace. You can salt it, you can save it, you can deploy it like you regularly would. All you have to do to deploy this is we use the test prefix there, so there are this set of test objects that get generated, and the DLL you'll have to ship with your application to make sure it's in the right location. And then you'll be able to ship your Co-dfns compiled products within your workspace and whatever you want to work with. And the basic idea is that once you've got those prerequisites installed, and those are mostly automated, you just want to pull up the workspace and start compiling, start working, try to make it as easy as possible for you guys to get started and get running. So in addition to try to make it easy to use, one of the components to making this stuff easy to use is you actually have to support APL. And so last year we were making a good push on supporting stuff. Now we're pretty much at a near feature complete status with respect to basic flat array primitives. So pretty much all of your core array primitives are going to be supported. You don't get matrix divide right now or matrix inverse yet. So the domino isn't in there. But pretty much all the rest of your primitives are in. There are a couple other minor limitations, like you can't use duplicate axes and transpose right now. Actually, who uses duplicate axes and transpose? All right, Roger. We got 1, 2. Skulls. Adam. Yeah. So they are. It's a known problem. I'm working on it. But right now you can't do that. You can't use error guards right now, but you can use branching and recursion with your dfns and your if statements, that kind of thing. You have a number of integer types are now supported, including 8-bit booleans. Sorry, Marshall. 16-bit integers, 32-bit integers. You've got 64-bit floats, and user meeting special. If you go to and get the user meeting special of the release, the 09.2 release, you get complex numbers with an FFT quad system function for you to run if you want. So you can play with your FFTs. You get all the basic compiler optimizations like recursion, function inlining, constant propagation, constant folding, dead and useless code elimination. You can run this on an Intel, OpenCL, or CUDA backend. So the CPU, OpenCL will work for pretty much every computer, but some people have reported stability issues on Linux because of the AMD drivers. It doesn't happen all the time, but apparently for some people that's an issue. The CUDA backend tends to be the most high performant, but if neither of those two happen to work for you, the Intel backend will run using the Intel MKL math libraries and things like that. That's the slowest option. Both the OpenCL and the CUDA backends will try to leverage some parallelism on your machine or use your graphics card, even if it's just a dinky Intel embedded graphics card. There's, since last year, there have been a number of new optimizations and tricks put into the primitives, things like making sure we do nicer things when you pass scalar primitives to operators, and scalar with reduction or different things like that. And we've improved the reliability and error reporting so that you are. It's getting to the point now where I'm having trouble easily crashing the system. So that's sort of a good place to be, where I need other people to find bugs now because I'm having trouble finding them. And we've made sure that if you get errors on the GPU, like let's say you try to allocate too much and there's just not enough space on your GPU to do that, you're going to get an error inside the workspace instead of crashing or getting an exception flagged or bringing your machine down or anything like that, which is good for GPU programming. We have, we're adding some built-in support for some things that people like to do. So FFTs is one example where you have a quad FFT function now so that you don't have to necessarily write that yourself. We try to make those fast if we can. We also have a new support for high-performance interactive exploration of some of your work. So I'm going to be demoing a little bit of that. The caching API is now easier to use as well. So the caching API is what allows you to incrementally move your application over to the dfns library. So what you would, or a dfns version of the code, what you would normally do is try to pick hotspots and then turn those into dfns and put them in their own namespace and compile them with Co-dfns. But sometimes you've got those hotspots are running in a loop. And every time you run that loop with the internal hotspot, you're copying data back and forth from the GPU, which is potentially a major performance bottleneck. So if you use the caching API, you can run that hotspot, and all the data stays on the GPU until you finish that loop, potentially, for instance. And then you can pull the data off of the GPU only after you've done all the additional computation. And we use some of this, we use this in some of the benchmarks in order to get performance on applications that are too complex at the moment, or they make heavy use of nested arrays or things like that. And then, of course, easier installation configuration. The limitations file, if you are in the source tree, there's a limitations file that you can read. And this will have things, this will show you a complete listing of the limitations based on what we currently see as priorities. So, for example, binomial over negative and floating point values is not implemented yet. One of the biggest limitations right now is you can do bracket indexing on a vector with a single element, but you can't do the semicolon bracket indexing. You can use squad instead, and you don't do assignment. So indexed assignment or those sorts of things, those are all pure functional. The compiler right now just works on pure functional code or denotational code. So unfortunately, I haven't implemented the @ operator yet. So that's a bit of a limitation. You really need to work array at a time in this. And user-defined operators are not there yet. And then, of course, we've got some other stuff we're working with. So moving forward, this is something I kind of need feedback from you guys on. There's a set of potential new things that we can work on. And in terms of what we prioritize moving forward for next year, what things we really want to. From my perspective, nested vectors, trains, and maybe indexed assignment are very likely to be high priority in terms of what we focus on. So I've come to the conclusion that I just want nested vectors. And so they're probably going to be going in there. And it's looking like character data type, at least one type of character data type could be added if there's enough demand for it. At the moment, there's no demand for it. So if somebody wants to use the Codfns compiler over character data, let's let me know so we can actually implement it. And there's the new 16 and 15 operators like the stencil and other things like that, which I would really like to put in there. And I think if people would like to leverage the GPU well for something like stencil, then we should put it in there. And I think it would be a nice fit. And additionally, there's this new idea for a mechanism for allowing you to sort of get a little bit more control over how you write things to the GPU, which would actually give an implementer more direct access to writing the kernels that they need to execute in parallel, but it will also permit certain optimizations for certain types of code. That's a piece that might show up as well. We also have two children or sibling projects called the Mystica project and ApixLib, which are a cryptographic stack and a picture library built on top of Codfns that we're working with. And Eric Wallace is currently sort of leading the charge slowly on the Mystica project, where we're really trying to use Codfns to create a better Libra SSL, if you will, or a better cryptographic stack, big number library support, things like that execute on the GPU. And then this picture library is designed to help when you're teaching people how to code, or if you just want a high performance image library on the GPU, you can use this. It's sort of plug and play, designed to allow you to easily edit and hack it to adapt to your own needs. So reliability, this is important. It turns out people don't like it when your system just crashes on you. And unfortunately, the state of GPU programming is such that very often the thing that applications do when the GPU fails is crash. Now, it's rare that it'll completely take down the machine, but I think, Jay, on your system, the graphics drivers are involved, right? So those are usually inside of the kernel. Something messes up in there, and you can bring the system down. So we've been working on trying to improve that reliability. So in particular, GPU errors are caught in a useful way now, at least as many as we can. And so you can deal with those errors more reliably, and you won't bring your whole system down. Your workspace will continue to work just fine, and you continue on doing what you need to do. And we're also doing we've got a little bit better support for data types and the overflow conditions. However, in the GPU, you're going to have to deal with overflow yourself. So if you do a sum reduction over something, you're not going to have to worry about overflow. But if you use plus on a giant vector of integers and you put those together, make sure that you handle overflow there, that you're not blowing things up. So with the reduction case, we can sort of do a little bit of that for you, but you're not going to get the automatic type promotion that you get in Dyalog right now. So of course, let's demo it by breaking it. So in here we can change this little guy here. Let's erase this and let's start with a new one. Let's say maybe we do an outer product multiply over two things, and That seems pretty simple, but then we can pass it a lot of data, and I don't have that big of a GPU on this machine, so what would be a good size? I guess 1E9? All right. Let's see if we can break it. Or Dyalog could take a long time to run. Yeah. So we get this error. This is an error you can copy and paste to me, for instance, but this line tells you most of it. I'm out of memory, but I haven't crashed, so I could continue. I could rerun this with something more reasonable. And I'm going to get results. And so now I can continue my work. I can keep going. I don't have to worry about everything coming. The sky is not going to fall down when I work with that now. So performance, of course, is why you're using the GPU. And we've been working on that as well. So one of the things that I've been working on is making sure that you guys can get performance out of your code yourselves without me having to help you too much. So this is an important thing. So the Co-dfns compiler has always been written with the idea that you'll have a predictable performance model that you can work off of without having to become an expert at the CUDA programming. Now, you will have to learn a little bit about how the APL system performs on the GPU. That's sort of unavoidable. And to help with that, we have this cheat sheet. So again, with like the limitations document, we have this cheat sheet here that shows you sort of how to begin thinking about your problems, how to approach your optimization issues, and things like that. One of them is you're going to have to get a basic idea of how the GPU runs, like you have a basic idea of what the CPU does when it's running things. And then you're going to have most everybody's heard a little bit of something like, oh, this is linear time, this is quadratic time. There's a sense of how much time something takes to do work on the CPU. With your GPUs, you're going to need to gain a bit of an intuition on what the ideal optimal performance in parallel algorithms is. And so the critical path concept is something that you're going to have to work with. And this document will help walk you through that. You can look up more on YouTube or Wikipedia or your algorithms textbook that's collecting dust in the back of your bookshelf. Something like that will help you to sort of get that idea. But in addition to that, we've got some general guidelines, and then this is your cheat sheet for performance, where when you think about execution on the GPU with APL, this cheat sheet helps you to think about the overall performance in really rough terms of each of your operations. So there are these embarrassingly parallel numeric operations. Those are going to be ideal performance. They're critical path, sort of the absolute minimum amount of time that they really have to take on an ideal machine is 1, because they're embarrassingly parallel. Theoretically, if you had an infinite number of processors, you could do everything in constant time. And they generate a certain number of GPU kernels. And GPU kernels is a big thing that you're going to have to remember, because the more kernels you generate, the slower things go. Kernels are like your giant, big, launching an isolate kind of concept. It costs a lot to launch a kernel. So these operations are likely to be fused when you work with them. So if they're put next to one another in your source code, they're likely going to be fused together so that they only generate a single kernel. And then some things are embarrassingly parallel, but they don't get fused. And down the line, some things are in the same complexity class as they are on the CPU. And so you can use those similarly to how you would use them on the CPU, understanding their performance behaviors. And that's a lot of the structural primitives that are just copying data around. But, and this is important, some functions change their complexity class when you start going onto the GPU, and their behaviors start to behave very differently. So replicate, for instance, is kind of linear, basically, more or less, on the GPU. You can just waltz right through it, select stuff out, and you get your results. You cannot do that on the GPU. So it ends up becoming a more complicated algorithm. You have this tree reduction of things that are happening, and you begin to get this different structure. So you have to recognize that those operations become inherently more complex. They do gain parallel speedups. You can actually get more performance out of them, but their complexity has changed. So you've got to be aware of that. And operators similarly have this issue. So the biggest thing with operators is you want to try to use as many scalar functions as possible. Because if you use the scalar functions, you're going to get better results. And then there's more details to go through, and I can help people to go through this and understand it and work it. But you've just got to remember that you can't pass an arbitrary user-defined function to an each and expect your performance to go well if you've got a billion elements to each, because you're going to generate a kernel for every single one of those elements, and then you might as well be generating a separate Dyalog interpreter instance to evaluate every single scalar. That's the scope of what you're doing. And it's, these are the kind of things you'll have to remember and keep in mind when you work with the code. So let's play around with it a little bit. So in addition to the regular source code to help you out, there are a set of benchmarks that you can play with. Not all of these have been fully updated to the newest version of the compiler yet, but a number of them are. So for example, we have our classic black shoals example, and this gives you an idea of how you might drive the compiler. So we have the namespace script up there in the S variable, and then we're fixing it. This is the caching algorithm stuff that we're using, caching API, because we want to bench against the caching API. So you can load one of these in. It'll compile it, get it ready for you. And then you can start running it. Now, remember that GPUs have a warm-up time. So when you initially launch them, you're going to have some configuration time to get things set up, and then they start chugging along, and they start being able to move and do some things. So what we're looking at here is the time that it actually takes to run the kernel, then the time that it takes to run the kernel and transfer the data back and forth for this particular application against the Dyalog version. And so you can see, not only does it take a little time to warm up, you have to give it enough data to where it can start actually using all of those parallel processors, and where memory bandwidth and things like that can begin to really take hold, and then you can start going faster. Now, I'm demoing this on my laptop. It's not the fastest processor in the world. It's got small amounts of memory, so I'm not going to be able to show all the scale of what you can do. But this at least will help give you a little bit of an idea of some of the stuff you can do. So we can get some increased performance for black shoals. Let's see, what's another fun one? We have, so I guess Martin was talking about neural networks. So we've got a little tiny neural network demo, which is basically the sigmoid forward feed micro benchmark that Romilly had been talking about. So we can run that as well. And all of these benchmarks work in the same way. You load them up, you let them run. And you start working on it. And so again, there's going to be a warm-up time with any of these little pieces. And then we can start chugging along. And it's going to take a little bit to work the data in. This number here is the size of one edge of the square matrix that we're running on. So this is a 128 by 128 matrix that we're going to test. And then we bump it up and we bump it up. And you can see here, the times are relatively constant at this low end because essentially we haven't yet filled things up. We're still working on getting them going. Now we're starting to be able to catch up and do something a little faster. And in this particular application, we can scale a little bit better. So as the numbers bump up, we start to be able to see faster speeds. And what's another fun one? Oh, okay. I know. I guess we should do Marshall. So I can only run against 16 right now. And unfortunately, the data types mean I'm inherently using probably 4 times or 5 times as much memory as Marshall's implementation, so that's a little bit of a disadvantage. But I wrote this one up just because I needed to, you know, I had to for myself. So there's some work to there's some work to be done here to improve the performance for this particular benchmark, but you've seen this one, so we'll see where we're at. So not too good yet. Let's see if we can do something here. All right, it's a little better. Let's, come on. All right, so we'll finally be able to begin to see some potential speed ups. All right, we can beat 16, but that's still a far cry from 17, unfortunately, at this point. So when it comes to Boolean operations, the Dyalog team keeps me working hard because they're always making their Boolean stuff faster. And so there's a lot of potential improvement here. I could probably double or triple these numbers if I got my data types down a little bit better and things like that. So I'm looking at improving that. But you know, they've got some pretty fast algorithms on the Boolean stuff, and so I've got a lot of challenging benchmarking stuff to work on with that. Let's see. Oh, we do have a built-in FFT now, so oh, I guess I should probably show you how you use it. As you would expect, say quad FFT, and you run FFT. Now this one we're benchmarking against the FFTW libraries in C that Nick kindly provided. So this is going to be the kernel version, the sort of industry standard C version, and the Co-dfns version with the data transfer overheads. And what this should immediately scream to you is that keep your stinking data on the GPU and don't transfer it back to Dyalog unless you need to, because the potential performance benefits there are huge if you can keep your data on the GPU. So the more work you can do on the GPU and not do your copies back and forth, the better. And so we're able to even with the data transfer overheads, we're able to begin outperforming the standard serialized version. Come on. Yeah. So it gives you a little bit of an idea there. Was this? Let's see, any other benchmarks you guys want to see? Let's see, what do we have? Oh, inner product, that's fun. Oh, game of life, yeah, we're going to have to do that one. I don't think I have time to do it. I can't resist, okay. If you guys just do matrix multiply, this is fun. So, unfortunately, this benchmark is set up for my big machine at home, so I can just do the tiny matrix stuff. I can't do the big one. Oh, did I? Oh. Thank you. All right. Yeah, so we'll just do the one version. So, and I think I can't do that many. I don't think my processor will handle all of that on this one. But these are doing some matrix multiplies. This is testing the kernel. So the GPU versus the Dyalog version. And on this one, we can do pretty well. Even on relatively small values, we can begin to outperform the Dyalog version by a fair amount. But again, this is not taking into account the transfer costs of the matrix, so you'd have to take that into account when you're working with this. So I like that number. That's a good performance number. And of course, we'll have to, oh dear, don't save. All right. And of course, we have to run the game of life because I can't help it. So this is an example of how you might have to adapt your code. This was just, I did this really quickly last night because I wanted to have a game of life example. So we've got Scholes' version, which is very nesty. We don't have stencil yet, so we're stuck there. But we can convert this out and make it flat array based. And you'll notice I played an optimization trick by keeping all of my scalar operations next to each other and doing all the rotates beforehand. That way, I can fuse that together, and so that SM line is probably only going to generate a single kernel, and it'll probably fuse with the next line after it, so we also generate only a single kernel there. So again, you're seeing a pattern here. Small amounts of data, don't run it on the GPU. And again, these are for square matrices. So this is a 128 by 128, 256 by 256. And then we begin to start catching up. And now we start winning. And I always love to see the percentage signs go into the hundreds. That makes me feel good. And I really like when they go to the thousands. All right, so now of course game of life is no fun if all you're doing is a bunch of boring graphs. So keep this in mind, we'll get back to it. Oh, I went all the way up to 8,000, okay, weird, all right. So anyways, one of the things that you guys have heard me talk about is the whole exploration of data, the value of data logic, things like that. And I know some of you, we've talked at this conference about interactively being able to look through your data, being able to see your data. And right now, I've begun to explore that in the compiler and try to make it possible for you to do some real-time interactive exploration of your data as well as just running the compiler stuff. So this is sort of beginning for me to move in a direction where we can have this majestic 4D interactive environment that makes it possible for you to just scrub in real time through all of your computation and visualize it in the sky with your HoloLens floating into the air and, you know, all that stuff. But right now we're not quite there. So in the game of life, we have these two life functions, the Co-dfns ones and the regular ones. So what I have is you can do Co-dfns graphics init, and then we can begin to have some fun with it. So let's just do game of life dot dialog life omega, and run that to a fixed point on a random 248 by 248 Boolean matrix. And so you can start visualizing your data. And we support imaging, histographs, plotting, multicolor RGB data, etc. So this is a version of running this with the Dyalog version. But if we save this, we can sort of compare the visual differences between running the... Let's see, how do I... Uh-oh. All right. And then run X on that. Yeah. So this is the Dyalog version. And what you should pay attention to is sort of the color of the screen as it goes. That's our performance. And then we can switch over to the Co-dfns version. And this, it doesn't have a time limit on it. And so you can begin to see it changes significantly faster because our frame rate, we're going quite a bit faster. And so the population is changing at a much faster rate. So, let's see, yeah, okay. I don't have much more, but there's a challenge for you. This little guy here, we can make it colorful. So how about we make it colorized? Instead of passing a Boolean, we just have to pass a rank 3 where the last axis is the RGB, so it's 3 column, or the last axis is 3 as its dimension. So does anybody know how we might randomize that to create this Technicolor version of the game of life? Oh, come on, APLers. Nobody? Is it just the morning? What? We could take the 3, we could turn it into a flat version and do a transpose on it, and then a 255 times that in a random value, right?
That would still be gray, right?
Sorry?
That is gray?
Gray? No, color.
RGB are equal?
RGB. Yeah. What's the point of what? Well, I mean, we don't have that much time. But we can make it funny colors now. Well, you can come see it on my screen then. But, yep, so that is what I have. I'm happy to take questions if we have time.
Are you looking at doing the key operator and interval index?
Key operator is an essential one that's going to go in there. You said the other one was?
Interval index.
I'm very intrigued by interval index. The monadic index underbar is practically a shoo-in. The dyadic index underbar, I would like to. I'm trying to find an excuse to implement it. The excuse I need is for it to be some high performance necessity inside of my compiler design. If I can find a reason to use it there, then it's definitely going in. Yeah. So, yeah. Yeah, pretty much all of the new operators I heartily enjoy, like, and approve of, and they are likely going to be going into the compiler, if only to convince you that you should use them instead, so they become the pathway to performance. I sort of want the @ operator to have prefix agreement because it's useless to me without prefix agreement, so I'm kind of holding out until Dyalog is willing to sort of step their foot into that pit of quicksand and say, yes, we'll do that, and then I can implement @ the way I want. Until then, it's kind of, yeah. But any other questions? And you can come see me anytime. We'll get this running. We'll play with your code. We'll set it up on your computer. I can demo the histogram stuff, anything like that. The histogram stuff is really interesting for statistics. Like if you're teaching statistics, you can do real-time modeling and show how the distribution changes over time as you're doing sampling or things like that. So that's a fun one, but yeah.
Okay, thank you, Aaron.
Right.
We're going to take a